So I'm happy to give the tutorial talk. I hope it's enough tutorial, but anyway. I thought already that some people give a nice introduction, so I luckily don't have to explain the Berry curvature. So everybody knows now what a Berry curvature is. Okay. So good. So just now I'm super excited about chirality, and I share this excitement with Angel, and hopefully more people from Hamburg. Anyway, so and I think we still see only the top of the iceberg in the field of topology, so I think it's still a lot to go. And so can we make a connection to, he likes it, okay. So why I'm so super excited about chirality is there was in 2021, postponed from 2020, symposium, a Nobel Symposium on chiral matter organized by Frank Wilczek. And these are only the European part because American were online at this time, still not available. So like people like Fang Ong and Ben Feringa was online and so on. So, and it was a symposium which was reaching out from biology and like Ben Feringa, also motors, nanomotors, up to high energy physics and astrophysics. So it shows that there is a big bridge between these fields, and topology, I think Frank Wilczek thought is somewhere in the middle, and it might help to explain eventually many areas, maybe with the same physics, okay? So therefore, but chirality itself, I think I also discussed this with Nicolas Baldin, for example, there's no figure of merit for chirality, and so she has now also a very nice paper on chiral phonads in Nature. So there's, I would say, still a lot to do, okay? And the idea is really so that I could also start the movie, that fundamental broken symmetries, I'm not sure whether it works here, probably. Fundamental broken symmetry is related to chirality, and we have chirality on different scales. I want to talk a little bit about the chiral anomaly. There's still eventually not yet a smoking gun experiment done for the chiral anomaly in wild semi-metals. There is some debate still. Always if you do transport, people think, okay, transport is really a direct method. But so one experiment was proven the parity violation in the weak forces via the beta decay of some cobalt atoms by Wu, and the theoretical prediction got Nobel Prizes, but also the origin of the life and the origin of the universe is still an open question, and they're both related to chirality. So we know we are all made only by one chiral molecule, okay, so only by one chirality, and nobody knows how the symmetry was broken. So where was the first chirality or chiral molecule, and why, and how could this happen? There are some people, so there must be a process where you put achirality in and get chirality out, okay? And some people, I don't talk about this today, think this is related to chirality-induced spin selectivity. People see spin polarized, strongly spin polarization in chiral molecules and chiral system, but it's also under debate in a similar way like the chiral anomaly, which is one way to explain. So if you have the Dirac equation, so to explain the asymmetry between particles and antiparticles, which then is seen in white semi-metals for electron and holes, or Dirac semi-metals in a magnetic field. So this is also not proven, and the experiments in high energy physics and astrophysics related to the chiral anomaly are on their way, partially with big instruments like CERN. They do heavy ion collision. So it's really something which is fundamentally interesting and exciting. And as I said, this is the one experiment which is really proven, and Li and Yang, for their theoretical prediction, got the Nobel Prize. Who was not considered, who did the experiment anyway. So I think some people from the Nobel Prize committee mentioned that this was for sure a mistake. Okay, so why I think it's even very interesting for this community is, like, I think because we can maybe also think dynamically about these things. And one thing is because recently, and here are some people in the audience who already have shown that we can have eventually 2D materials or cargo lattice where we can switch chirality by light or magnetic field. So this is here a symbol for this, like, for example, iron, germanium, cesium, vanadium-3, antimony 5, or tantalum sulfide. They show charge density waves, which are eventually chiral. So we can maybe really have dynamically different structural chiralities, and we learned today also in the first talk that this small changes in structure can be big changes in the properties. But the question is, can we also switch the electronic chirality? Yes, in bisemi metals by applying the E dot B term, so it's also dynamically. So can we think about even better, maybe smoking gun experiments for the chiral anomaly? So I will explain the chiral anomaly in my beginning. Maybe for some it's boring, but then it's also like what people like to do in correlated physics. They like to tune knobs and look for the interplay between structure, electronic structure, phonons. Maybe I mentioned already this nice work about the chiral phonons of Nicola, magnons, etc. pp. So I still think that there's a lot to do because it was not done in the past. Everybody works on correlated oxides, but not on chiral systems. One problem is for sure that we have to get the materials homochiral. But here we can tune the chirality. Unfortunately, I have a little bit of problem. Anyway, I might have to go here. Anyway, so on the other side, yeah, I said I want to mention that there is already very nice work with from the audience here about interesting properties by applying chiral light, for example, on this 2D materials with chiral charge density waves or iron germanium. And I think one thing is also, I would say, we maybe have overlooked many interesting chiral structures because it's also a question of the quality of structure determination, okay? And some of the materials show phase transition at lower temperature, so they're sometimes seen even in transport that you see a phase transition, but otherwise I would say there may be more interesting materials out there and more chiral materials out there, because if we think about space groups, so 30% of the space groups are chiral, but only 10% of the materials so far are discovered to be chiral, okay? So it's still, I think, something which is maybe overlooked. Okay, on the other side, we have now the field of topology. And here we really see how important symmetry is, what we learned already in the first talk. So symmetry can determine whether something belongs to the class, the trivial class or the topological class. So simply by giving a number or a topological number to the electronic structure. And I think we don't have too many students here. I don't have to explain it, but we all know that we can characterize now the electronic structure by this topological numbers. So here like 0, 1 hole, 3 holes, etc. And so this is a totally new way to determine electronic structures and materials. And so I think it's related. All the story started with the quantum Hall effect, where we have chiral or edge states, where the electron and the spin is sometimes anyway connected, and with the very nice Nobel Prize for Haldane, who recognized if we have a quantum Hall system, we need a large magnetic field. So if we have magnetic materials, we should have an intrinsic magnetic field. So we should find also quantum Hall effect in magnetic systems. So this was his prediction, which then has led to the Nobel Prize for topology, which was not so obvious clear for me at the beginning, but now I understand the connection. And later, with the, for us, more important paper where they predicted the quantum spin Hall effect in graphene based on spin-orbit coupling. And we already have heard today how important spin-orbit coupling is in several talks. And we had this very nice talk about also the meaning of the band inversion and the Berry curvature. So we learned already that we can have trivial semiconductors with a valence and a conduction band, that we can have crossing points in the electronic structure, which can become forbidden crossing, and we get our barrier curvature out of this, and so we have interesting topological materials. And everybody knows here in the audience, I think, that we can have simple semiconductors which are insulating in the bulk and the surface, and we can have topological insulators where the surface states are metallic. But the interesting thing is that here the spin and the momentum are locked, so we have chiral electrons at the surface, and I think this is something which is very interesting. And if you look in the band structures, and not only where the Fermi energy is just here, so in all metals we see all these crossing points between bands of different parity, so it's not surprising that so many bands are claimed to be topological. So in this last paper, if you allow the Fermi energy to move around, so you can more or less say, I think even some people claim sodium chloride, a really insulating insulator, is topological, but I don't see experiment in this direction, but more or less if you move the electrons, the Fermi energy around, so we can say, so more or less most of the materials have some topological properties if we allow doping and so on. And if you do excited states like in with light matter interaction, you anyway can shoot the electrons everywhere. So it's simply interesting. So, and I really like the idea to make the connection between, and I think Angel too, no, you agree with me, to make the connection between if spin and momentum is locked and our electrons with the chiral molecules. And at the end, I come also back to the chiral molecules because I'm doing more now with people who try to make chiral molecules. So every carbon atom which has 4 different ligands is chiral. So there is a big number of organic molecules which are chiral. So you can have 2 versions of the molecules. And this is like the right and the left hands. You cannot bring them together. So they are really distinguished. But the only way to separate them in the real world is like, it's very difficult. So I think, and since you are all made by chirality, so all the pharmaceutical industry depends that they can make molecules with 1 chirality. And this is very difficult so far. So most of the production happens that people make both chiralities because this is automatic. If you put some molecules and atoms together in a pot and you have a chemical reaction, you get exactly 50-50. And then there's a difficult separation process by doing an additional chemical reaction only with 1 chirality. Or there's, so you have to put chirality in a chiral catalyst, and then you are able to synthesize 1 chirality, okay? But it's a very difficult and expensive process, but it's necessary since you are not only able, if you want to give energy to your body, also the sugar is chiral, so you can only eat 1 chirality. The other chirality is not only bitter, it's useless for your body. In the same way, every medicamentation is chiral, more or less. So therefore, I think it was not surprising that there are already 2 Nobel Prizes on catalysis with chiral molecules, and the one was last year Ben List for homochiral catalysis with small molecules. Anyway, so we in topology knows that it's also super exciting that if our spin and momentum is locked, so the electrons don't get backscattered. This is a very nice movie with, which Maria has. And my dream is now, and I think also Angel's, we should let the topology and the electrons maybe, can they talk to maybe to more than maybe to molecules, and can we use maybe chiral phonons and so on to break fundamentally the symmetry. So, so we already talked about the chiral electrons on the surface and the chiral electron at the edges in case of the quantum Hall effect. Today also in the last talk, the white semi-metal were discussed, so we can have this degenerated point. So if we have this overlap between the valence and the conduction band, which we already had, and we have a forbidden crossing area here, so we lift the whole crossing and we get an insulator. But if there is, for example, if there are rotation symmetries, we can have still these degeneration points, and depending on the crystal structure, the symmetry essential, very essential. Whether we have inversion symmetry or time reversal symmetry. So we have Dirac semimetals, or if it's broken, we have Weyl semimetals. And the Weyl semimetals are more or less, you lift the degeneration of a Dirac semimetal, and you get this different, we already saw the Berry curvature, which can be having different signs. And here then we have two crossing points which have different signs. So we have chirality in the bulk in the momentum space of the Weyl semimetals. So therefore, the Weyl semimetals has drawn a lot of attention. And so I already mentioned this has even motivated Frank Wilczek to have this chiral meta workshop, where there were many talks also related to the chiral anomaly, so which is fundamental broken symmetry, to explain, as I mentioned already, the asymmetry between particles and antiparticles. And the corresponding experiments in the solid were also developed by, for example, in these papers, to show really that we can have here a fundamental broken symmetry. And it's only possible in the quantum world. It's not possible in classical world. And this is more for students who we are not dealing with, or for the general audience, we are not dealing with matter and antimatter. We are dealing with quasi-particles always in a solid. So, and in transport, the experiments are quite indirect. I have a few ideas how to maybe have more smoking gun experiments than maybe what we did so far. So far, if we want to do then the experiment in a solid, we have to investigate the chiral anomaly in transport or in thermal transport. There's an analogy, the axial gravitational anomaly, which you can show in a solid, so you can make the asymmetry even starting with the symmetric case by applying the E dot B term in parallel. So the magnetic field, the thermal gradient, and the electric field in parallel in material. So I think for most of you it's a little bit boring, but I told you this is interesting. By switching the electric field or maybe chiral light, you can switch more or less there the sign of the in transport, etc. And this is exactly what many people did. We did it for niobium phosphide. Other people did it for tantalum arsenic or for gadolinium platinum bismuth, the Heusler compound. So you can see if you change the B field from like in a Hall measurement from out of plane to in plane, so you see that you change the sign in transport. Okay, here we would say in case of this niobium phosphide, we really are quite sure that we have no current jetting because there is no giant magnetoresistance effect in this nanowires. But this is one of the still debates why I think there was some debate even at the symposium whether this is now really proven or not. Okay, the same you can do in thermal transport, which is really a more difficult experiment, but you also see a change in the sign here in the thermal conductivity in this. Okay, anyway, this at least brought our paper, the thermal transport, into the New York Times, but since recent day we know, don't bring your paper into the New York Times, it's the negative. Okay, only if you believe in room temperature superconductor. Anyway, but this experiment were done also in several other systems, like the gadolinium platinum bismuth, for example, or by your Ceremans in bismuth. He tuned the bismuth exactly to be at the Y points, and in bismuth he claims he has a much cleaner band structure, even it doesn't look totally clean because you also have to have a certain field to see the chiral anomaly. And I think, I hope Susanne will talk also about, at least in cadmium arsenic, you can also show it. And here you see also that still the Wiedemann-Franz law is not violated. So you see it's really, I would say also, it's maybe a sign for non-current jetting. And you see it also in magnetic system, even there the effect is also not so giant. Anyway, so as I mentioned, there are many chiral space groups. 30% of the materials are chiral. So is there something interesting in the context of topology? One thing, as I already mentioned, so why are chiral materials not so heavily investigated, and why are we drawing much more attention nowadays? Is also, I think I would say the methods are better to do a careful crystal structure characterization. We sometimes go also to lower temperature because all the crystal structure data, so also where we try to our high throughput calculation is based on, is mainly on the simple crystal structure in the database, and they are very often made by powders. So they very often have not really the right crystal structure, and it's not a temperature-dependent crystal structure. So I would say there's a lot to do still on the crystal structure. And in the same way that it's very difficult to make homochiral molecules, it's the same problem with crystals, okay? So make only one chirality is very difficult. So, so very often you get simply both chirality because there's no energy difference between them in the same way as there's. So I think, and there's so far not really a simple recipe. So one of our biggest effort now in the group is try to grow homochiral crystals and try to do it in different ways by also trying to use advantage of chirality-induced spin selectivity or some strange theory. So maybe growing on a magnetic substrate, it's easier, blah, blah, blah. Anyway, in films, one can use a substrate which is chiral, so it's, but it's also here, again, also difficult to determine then the structure. Anyway, it's still interesting because beyond of Y fermions and Dirac fermions, so in chiral systems, we can have these chiral fermions which have even the advantage. So what we showed here, if you apply the E dot B field, you can slightly change the position of the two Y points. Here you have it naturally in these chiral fermions, and therefore it's maybe interesting to learn something from here, what we could then do maybe dynamically there or vice versa, so to see maybe more interesting new physics. And this was also what Carlo Bena, he cited, that Heisenberg himself thought, so the solution of the Dirac equation, the Dirac and the Y solution is the only possibility for high energy physics, industrial physics. But if you have a solid Gitterwelt, so then you could even see this other kind of fermions, this unconventional fermions, and maybe there's some interesting physics behind this. So I told you already, it's very tough to synthesize homochiral crystal, and we put a lot of efforts. Just now we tried, especially with tellurium, because the synthesis temperature is not so high. So because one possibility is simply if you start with a seed, so the most famous method to do solids, real solids. Organic crystals is a little bit different, so that you have a seed where you have a well-defined chirality, and then you hope that the chirality don't switch during the growth process. But otherwise, we try also to put here seed crystals. But luckily, for some of the crystals, we are lucky. So even in self-flux, I have to say this palladium, gallium, and platinum gallium. So then you maybe know why we are mainly working on this, and platinum, aluminum. Luckily, we get a crystal, and so 30% are left-handed and 70% are right-handed. So this is luck. So far, it's not a very good synthesis method. But anyway, we try to improve with seed crystals, etc., as a technique. But it would be nice in organic chemistry, for example, but this happens at lower temperatures, so one can maybe put some small amino acids here, you know, but, and then you get the crystals also, so it's determined by the chirality of amino acid, but we work at temperatures where all the amino acids end up as carbon in our crystal, and they cannot help us to determine the chirality. But as I said, we now try to grow also in a magnetic field and stuff like this. We build new apparatus to get more chiral crystals to investigate. Because you can imagine also, I think, Andy, if we have not a homochiral crystals of a superconductor, we probably don't see really the properties, okay? And I think this is probably the problem. And to determine the crystal structure of the chiral crystals is also very difficult because it's a small structural difference very often. But there are some methods nowadays, and you know, if you have simply X-rays which shows you the chirality of this point, we don't know what happened there, okay? So with this electron backscattering methods, now it's possible to scan at least the whole crystal so that we can determine the chirality of a whole crystal, okay, to make sure that we really see. If we have this dynamic situation, but I think also I'm not sure how, like in tantalum sulfide, the dynamic charge density wave, if we can imprint a certain chirality with a magnetic field or with some chiral light, then it would be easier because we simply would imprint then the chirality. So we could learn something from this. Okay.
Can I ask a question here?
Yeah.
When you grow this homo-chiral crystal, is it like there are no domains, or is it all just one?
So the homo crystal seems to be more domainless because in the moment when you have the domain, there's the same chance that it has the other chirality, or there's no motivation, you know. So it's simply like this few crystals works like it works, you know. So this is also debate. So I think nobody also thought the thing sometimes to the end, you know. So quartz, for example, is chiral. So could be quartz the origin of life. Some people think magnetic materials. Anyway, so I think there's no really clear, and I think, anyway, so our idea would be if we could at the end show how you can make homo-chiral molecules and homo-chiral crystals, which are the methods beyond putting chirality in, would be great. Okay, anyway, so we already saw the wide semi-metals, and we know that they have Fermi arcs. And the difference, if you go then to the chiral material, so I already mentioned that then the degeneration points are at different points in the Bryan zone, and they are also at different energies. So they are more stable because they cannot annihilate each other. So a wide semi-metal could become, if you make it, if you can strain it to a high symmetry, a Dirac semi-metal, but this is not possible here. And the interesting thing is, for me, very interesting thing is that we have chiral surface states. And I think there's this prediction of the quantized circular photogalvanic effect. So I would say this is, I think, still one motivation for the optics people, as they should pay attention. I think this, if we really could show quantization, you know, this is a smoking gun experiment, okay? If we could show quantization even here by tuning, so this is like, I did some nice calculation with Jan Zhang, so it should be possible. So I think this would be really a smoking gun experiment for the chiral anomaly, or the existence of the chiral anomaly. Okay, so therefore we always get here these two pairs of chiral crystals, which should have then two different Berry phases, signs of Berry phases. Okay, so this is the idea. So in some sense, is this like a photograph of the two different situations, also of the chiral anomaly which we have here. Then, but here's the out of equilibrium, if you want, is much larger in these chiral crystals. Anyway, so if you go to real crystals, so as I said, we have the B20 structure. So far, we worked mainly on the B20 structure. But there are other systems, even the tantalum selenium iodide system is chiral, and tantalum sulfide and others eventually shows this chiral charge density. Many of the Kagomis eventually show chiral. So if this is a general scheme of the Kagome of a certain, if you have a certain, you know, the Kagomis have this Van Hove singularity, this flat band, and so on. And if you have to be at a certain point in the Bryan zone, you might get this chiral structural distortion. This would be cool. Then one would have many, many more examples where we dynamically could tune the properties. Okay, so we are doing a lot on Kagomis, but I don't talk about this. This is a very simple system. So we have this 4-fold fermion in the system and a 6-fold fermion system at the gamma and the R point. And so looks still complex. It's not a simple band structure, so it's not ideal for finding quantization. but for many other things, and especially in photoemission. So since I already said we have both different chirality, so we could see what we can see in photoemission. So, so the first thing, and this is all now the work of Niels Schröter, who is now independent scientist, MPGR in microstructure physics. So he does a lot, and he did a lot, and so this is his new field if you want to do photoemission on the systems. So you see the fourfold degeneration. It's quite a good agreement. You see a few more bands here, but they are related also. So this is spike and to the surface state, you know. And what was already published is that we can see the two. It's really difficult to see eventually, to see the two Fermi arcs here with the two different chiralities. And so you can also see here, this was another paper which showed that you have a Chern number of 4 in this material. It's more for the expert, so that you have a splitting of the Fermi arcs, and you have these two different slopes of the Fermi arcs on the two different surfaces of the two different crystals. So it was possible also to show this Chern number 4 in these materials with the two different slopes, which you can here see. Anyway, so that you really can distinguish these two crystals, and they have chiral surface states, and you have the Chern number 4. Okay, okay. But I still think, and this is very challenging, I know, so I like the work of the Würzburg group on circular polarized light, also where they did photoemission with circular polarized light. But I have this old guy here who came from a long traditional photoemission group with Gerd Schönhens and others, and they are very critical against using circular polarized light to distinguish the chirality of the crystals, because you have to be very careful, because you could imprint chirality where there is no chirality. So, but we think we did some experiments. So Mango did some experiments, and he sees really that the two different chiral crystals show with circular polarized light different responses to the circular polarized photoemission light. So this is the Fermi surface, and which is in agreement to the Barry phase curvature, which is also related to the orbital angular momentum. We already learned a lot today, so I think I don't have to explain too much. So, but I think there's more to do. I have the feeling that we learn more about the connection between Barry curvature and different chiralities. For me, the important thing is what makes it nice, because if I have a molecule, I only have the gamma point, okay? So this makes maybe to do chemistry and selective chemistry with molecules makes it more difficult. But if we have a solid, we have the momentum space, which gives us additional degrees of freedom, which we see even in the Barry phase and in all the other things. So maybe this is a tweezer to separate, or to learn how to separate, maybe even, or help the people working on molecules. And I have to say, already 2018, Ben List, he's an organic chemist, only works in liquids, organic chemist, okay? So he came to our group and gave a talk that he thinks topology maybe can solve this problem of asymmetric catalysis, okay? So it's very optimistic, but maybe with all this additional scissors, we maybe have a possibility. The other thing is, and I still think that we should work more on this, is the prediction of the quantized circular photogalvanic effect of Joel Moores and others. So which hope to see it nicely in the rhodium silicide, but I still think here we might have to find still cleaner materials to see really a nice quantization. Here we see a kind of plateau in this material, but this is because we have this additional bands crossing. And I also, this is a little bit also my discussion with the theoretician, if you have the ideal vial, which only has a crossing, I'm always have the feeling you will have you will open a band gap, what we saw also in tantalum selenium iodide. So this should be from the DFT calculation, the ideal vial, or it's more or less not so many bands crossing, a large band gap, but in the moment, then why should the system not lift the degeneration, make a small structural distortion, and become insulated? Or maybe due to correlation, I don't even know. Anyway, so all the things you can do with other members. So with Hassan, we worked on cobalt silicide and rhodium silicide. So we made this crystal too. So if you do photoemissions, the spot is small enough, the crystals still are homochiral over a certain range. And some people even claim now that this material show very interesting surface states, which are also chiral, or even there's still a lot to do in these materials. But already now very similar to also the other Kagome system. So some of the compounds like iron germanium, it crystallizes in the B20 structure and also in the Kagome structure. So it has a hexagonal structure, Kagome, same composition, and both seems to be having some interesting electronic instabilities. Anyway, I think there's a lot to come. And I think I was hopefully not too fast. So what we are now doing, also we try to play with the interaction between the interface between these crystals and homochiral molecules. And we started with dopamine. So because this is some molecule which you can buy in high quality and 100% homochiral, because one is used for Parkinson's disease and the other is biological inactive. And we could show that there is a asymmetric absorption on our homochiral crystal. So the crystal fits to the molecule, which I think is not so super exciting. But we also have grown films where we think they are quite homochiral crystals. And we see also here in asymmetry, you see there's a higher absorption from one of the molecule over the other, left-handed and right-handed dopamine. But what is also more interesting is that we see here also magnetic field dependence in these materials. Okay, maybe this could maybe also a way to even enhance or manipulate it. So what is the vision? And this is with Ben List's team. Also, we try what is our big vision. So one thing is we can show already absorption on the chiral crystals. So we can make homochiral crystals and do absorption. The good thing is if they have platinum and palladium, they are quite important catalysts in asymmetric catalysis, organic catalysis, plays also in the pharmaceutical industry a role. So having this in a chiral way is already interesting. But we want to also investigate other question. What is the role of the chiral surface state? Can we only use the surface state for absorption and catalysis? And there's a big group of people, they are working on this chirality-induced spin selectivity. They think that magnetism, so it depends whether my nickel is oriented like this or that. We can have homochiral absorption. This would be cool. Because this, but it's still under debate. So because then one could simply say, if spins induce chirality, it could be something that the question, what is the origin of life, was maybe magnetite, because there's a lot of magnetite on Earth. So this is one possibility. But what I would like to do, and we are working on this is not a trivial experiment, is can we use the chiral anomaly to get homochiral absorption by applying the E dot B term. Okay, so this is one. And the other thing is like what I already mentioned, all these materials. This is also to motivate maybe future work, where you can have a non-chiral structure maybe at room temperature, which has mirror planes, and then eventually at lower temperature, the mirror planes disappear, and you can set a certain chirality with the magnetic field. This was in the cesium vanadium antimony, but it's also in tantalum sulfide or titanium selenide. It was first done here with our friends in MIT. And so the proof to show that you did this symmetry, broken symmetry, is in this nonlinear transport measurement, this magnetoelectric effect, which we saw in cesium vanadium antimony. Interesting, it's not there in potassium. vanadium antimony. So I think it's probably not directly connected to the superconductivity in these materials. But anyway, it's interesting. So to do more of this nonlinear transport measurement and photo maybe transport measurement to really investigate and maybe even identify chiral symmetries in the electronic structure. Here's still the question, is the chiral symmetry in the electronic structure connected to the structure? Because we have a charge density wave, I would say we can say this, but I think, anyway, there's some discussion about this. Okay, with this, I come to the end. I hope I was not too fast, but I have a summary.